If you've ever wrangled with a database, you know that sinking feeling. Your query fails, and you get hit with some cryptic error message that looks more like a riddle than a clue. Well, today, we're going to demystify all of that. We're going to turn that chaos into clarity and learn how to read those errors like they're simple road signs. Ah, yes, this old friend. We have all been here, staring at the screen, seeing a message just like this. It's one of those things that just stops you dead in your tracks. It feels like the database is just slamming the door in your face, right? But it's not just a rejection. It's telling you something important. You see, these errors, they aren't just random noise. They are actually a structured language that the database uses to tell you precisely what went wrong. And once you learn to speak this language, you can stop guessing and start actually solving the problem.
So, how do we crack this code? Well, it all starts with understanding the systems working behind the scenes. Databases have these built-in frameworks to report problems in a really consistent way, and learning them is our first step. Okay, first up, meet SQLSTATE. The best way to think of this is like a universal postal code for database errors. It's this 5-character code, and it's standardized across pretty much all the big systems: Postgres, MySQL, you name it. And here's why that's so key. A descriptive message, the text part, that might change between software versions, or if the language is set to Spanish or German. But the SQL state code for a specific type of problem, that stays the same. For your apps, it is the most dependable way to figure out what kind of error you're actually dealing with. Now, some systems give you even more context. SQL Server, for example, it takes things a step further with what you can basically think of as a triage system. It uses severity levels to tell you not just what is wrong, but how wrong it is. It lets you immediately get a sense of just how serious the problem is. Levels 11 through 16, these are the ones you're going to see most often. They're your user-fixable errors. Things like typos in your query, maybe trying to access a table that doesn't exist, or permission issues. The database is essentially saying, hey, you made a mistake here, but you can probably fix this yourself. Now, when you see a severity level from 17 to 19, your job changes. These point to internal software or resource problems that you, the user, can't fix. This is the database telling you, hey, this one's not on you, but you need to go get a system administrator involved. And then you've got levels 20 through 24. These are the red alerts. We are talking about fatal system problems that will terminate the entire process. This could mean a corrupted database, a busted index, maybe even a hardware failure. This is a full-on Houston, we have a problem situation. So while different systems have their own ways of classifying how bad things are, most errors you'll actually run into fall into just 3 main families. And if you understand these, you'll be able to diagnose problems so much faster, no matter what database you're working with. And here they are: access, integrity, and resource errors. The analogies here make it super simple. An access error, that's like trying to open a door with the wrong key. An integrity error, that's like breaking a fundamental rule of the house. And a resource error, well, that's when the house is just plain full. Let's take a closer look at our first suspect: access errors. This is all about authentication and permissions. You know the drill. Your brand new web application tries to connect to the production database, but whoops, it's still using the default development password. Boom, access denied. The database is actively blocking you, and for a very good reason. And what's interesting is you can see how different systems talk about the exact same problem. MySQL gives you that infamous error 1045. PostgreSQL classifies it under class 08 for connection exceptions. And SQL Server, it flags it as a severity 14 security issue. They're all different dialects, but they mean the exact same thing. You don't have the right key. Okay, our second suspect, integrity errors. Now these are different. They happen when your command is perfectly valid. The syntax is fine, but the action itself violates the structural rules of the database. Imagine a user trying to sign up with an email address that's already in your users table. The database has a rule: emails have to be unique. So when that user hits submit, the database throws an integrity error to protect its own rules. For example, SQL Server will give you a super specific error 2627 for a primary key violation, which can happen if an app's internal counter gets out of sync with what's in the database. Postgres, on the other hand, it kind of groups all these rule-breaking issues, unique, not null, check violations, under its broader class 23 umbrella. And finally, we have resource errors. Now, these have nothing to do with your query's logic or your permissions. The problem here is the environment. It's what happens when your e-commerce site suddenly goes viral during a huge sale. Thousands of people try to connect all at once, the server runs out of available connections, and new customers start seeing errors.
The code is perfectly fine, but the system is just completely overwhelmed. Yeah, the most common culprits here are pretty predictable. The disk is full, there's not enough memory to process a huge query, or the server just hits its limit for how many connections it can handle at once. When you see these errors, it means it's time to check the health of the server itself, not the code you just wrote. So we've covered errors caused by your code, your permissions, and the system's limits. But what about errors that are nobody's fault? This is a really critical concept for building tough, resilient applications, because sometimes some errors can actually fix themselves.
I mean, think about it. What happens when the error isn't something you did, or the database, or a resource problem? What if it's just a temporary glitch in the matrix, a little hiccup in the network that connects you to the database? And this brings us to this idea of a transient fault. It's like a flicker in the lights. For a split second, the connection is lost. Maybe a router somewhere on the internet blinks, or a cloud service is restarting in the background. But a moment later, everything's back to normal. The key thing here is that if you just wait a second and try again, it will probably work. To handle these gracefully, your applications can use smart retry strategies. You could use a simple fixed interval, wait 2 seconds between each attempt. An incremental one is a little better, where you wait 2 seconds, then 4, then 6, but the gold standard is exponential backoff, where you dramatically increase the wait time after each failure. This is great because it prevents your application from just hammering a service that might already be struggling. So you see, an error message isn't an ending. It's really the beginning of a diagnosis. By understanding these systems, like SQLSTATE and the common categories of failure, you can turn that moment of frustration into a clear path forward. Honestly, understanding the system is your most powerful tool. And that leads to a final thought. We've seen that these errors aren't chaotic at all. They follow a strict, logical, and often predictable code. So, if that's the case, how long will it be before AI systems can not only diagnose these issues in real time, but maybe even apply the fixes for us automatically? What do you think that future looks like?